Hello everyone, good evening. This is lesson 12. So today I will announce arrangements for midterm exam. So I'll explain that now, and if you have questions, please let me know, either now or later. So we will have a midterm exam on Thursday, 5th of November. In usual class time. Topics of the exam. What we studied so far. So that's classes 1 to 11. So length of the exam is approximately 90 minutes because we do it in the class time. Method, because some of us are offline and some of us are online, we will do this using Learn. So questions. Released on Learn. At the beginning. And you should upload answers to Learn before the end. So same method as homework. So note, you may take in the lecture room if you can, for those who are on campus. Or online. And if you have a choice, you are free to do either. So the purpose so many things we study are used throughout the course. So functions, intervals, limits, and differentiation. So it is important you revise and practice these as we continue. Okay, so let me see if there are any questions. So, so question. So questions. So first thing, seeing the conversation on the chat. So please revise in groups. Ask each other questions. Seek help from TAs and myself. These are all good things. Okay. So about the number of questions. This is not decided yet. The style will be similar to homeworks. So about particular subjects tested, I make no comment. And also the percentage of the final grade is not decided yet. But about exercise classes, there will be an announcement soon. Good point about calculators. So let me make a note. So books not allowed. Calculators not allowed. So there is no invigilating. So we trust you not to cheat. So cheating is not an advantage in the long term. Well, for most of you, this calculus course will be used in many of the courses you do in your university time. So it's definitely to your advantage to study and understand as much as you can things, because so much builds on this course. But I should say, of course, if we find any evidence of cheating, we will take strong action. So finally, if you could do and you review the notes, you should do well in midterm. So if you have difficulties, now is a good time to ask for help. Okay, so I'm just going to check the WeChat group, see if there are any questions there now. Okay, so if there's no more questions, let's continue. Sorry, my writing is not so neat today. I'm using a different pencil. So I will tidy it up when I put the notes online. Okay. Oh, one more point about homework. So I will not set homework on October 29, week before midterm. So that week you can concentrate on reviewing what we already learned. Okay. So some review to start of the chain rule. So remember, the chain rule takes this form. So I find it easier to remember the formula and then write down the functions involved. For y is a function f of u, and u is a function g of x. So some simple examples. If y is u squared and u is x plus 1, then putting those together, y is x plus 1 squared. So let's write this out in functions as well. So y is fu, and u is gx. And then this is saying that y is the function g then f. We write that like that. So it can be a bit confusing because the function is g then f, but we write it as f circle g, but that's just the notation, so you have to remember it. And then we can use the chain rule to calculate the derivative. So dy by du, derivative of u squared is 2u, and derivative of u with respect to x is just 1. So the derivative of x is 1, the derivative of constant is 0. So putting those together, we get 2 times u, and that's 2 times x plus 1. So let's see why this makes sense. Well, if we have x squared like this, well, how to write this? So let's write y is x squared. Then the derivative is 2x. You can see this from the graph because for negative x, the derivative is negative, and the graph is sloping down. Let me draw this in, so y prime negative, but for positive x, y prime is positive, and the graph is sloping up. Okay, but now let's draw the graph of x plus 1 squared. Like this. Well, remember, if you have a graph and you replace x, the independent variable, with x plus 1, then that shifts the graph horizontally, shifts it to the left. So we get a graph like this. So this point, which used to be 0, is now 1. And what's the y-intercept? Well, that's 1 as well, just the value when x is 0. And now y is x plus 1 squared, and y prime is 2 times x plus 1. But that makes sense because when I go from x squared to x plus 1 squared, I shift the graph. And so y prime, the derivative, which gives the slope, is also shifted by the same amount. So in the same way, for x less than, oh, this is minus 1, obviously, x less than minus 1, y prime is negative, and for x greater than minus 1, y prime is positive. Okay, so that's just a little example of the chain rule. And there are lots of other examples like that. If you shift x and multiply x by something as well, then you can use the chain rule to work out the derivative. So there are some examples of that in the homework this week. So a new section in the book, it's called Related Rates. So if we have an equation which relates some physical quantities, and we saw some of these already. So for instance, time, position, area, volume. But also it could be something different like temperature. Oh, and I want to actually treat time differently. So let's say these quantities depend on time. Then the derivatives with respect to time are rates of change. So we can use calculus to relate their rates of change. So let me give an example to say what I'm thinking of. So the volume of a sphere is 4/3 pi times its radius cubed. Yes. Well, that's a small r. Smaller, yes. And then if I differentiate with respect to time, on the one side I get dB by dt, and on this side I have a function of r, and r is a function of t. So I can use the chain rule to differentiate. So first I differentiate the outer function, and then I differentiate the inner function, which is r. So differentiating the outer function, blah, 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 r cubed, we get this. And the inner function gives us dr by dt. So this is using the chain rule again. And now this tells us something that we already knew. So if we have a balloon, and we inflate, at a rate of 1 meter cubed per second. So that means we add 1 meter cubed to the volume every second. Then the rate of change of the volume is 1. Hence, the rate of change of the radius is 1 over four pi r squared. And for those of you who are thinking about units, you'll see the units of this are meters per second, because the 1 on the top is meters cubed per second, and we have meters squared on the bottom. So the units are what it has to be. And so, meters per second. So let's draw a graph of this quickly. If the radius is graphed against this rate of change, then we get this 1 over 4 pi r squared. So as r increases, the rate of change of r decreases rapidly. And we all know that if you have a balloon and you keep blowing it up, even if you're blowing at the same speed out of your mouth, the rate at which the balloon gets bigger starts very fast, it goes whoosh, and then it gets harder and harder to increase that radius. So let's do another example. So I need to find picture. Going back. Where are we? Oh yeah, okay. That looks like I might not have filed the picture in the right place. Sorry for this. Ah, here we are. Yes, so this picture. So this picture shows a tank with an open tap. If I open the tap, liquid is leaving the tank at a rate of 3,000 liters per minute. Yeah. So if volume decreases rate 3,000 liters per minute, what is rate of change of h, the height of the water? So we do this in the same way. We write down the relation between the physical quantities. So the volume is pi r squared, the area of the base, times h in meters cubed. And how many liters is that? Well, a liter is not a meter cubed, it's 10 centimeters cubed. So a meter cubed has 1,000 liters in it. So the volume in liters is 1,000 times that. So in the same way, using the chain rule, I can calculate dV by dt. So I get 2 pi r dr by dt. Oh, now I made a mistake. So What's the mistake I made here? Actually, in this situation, the radius is not changing. The height is changing. So radius is constant. So the right answer is that we treat r as a constant. So 1,000 is a constant, pi is a constant, r squared is a constant as well, but h is a function of t. So r is constant, whereas h is a function of t. And so, if this side is minus 3,000, then that implies that dH by dt is minus 3 over pi r squared. So let's say the radius is equal to 1 meter. Then dH by dt is minus 3 over pi. And so if you calculate that, it's approximately a rate of decrease of 0.95 meters per minute. Okay, so when we see that number, let's check if it seems about right. So we have a tank of radius 1 meter, diameter 2 meters. And we're saying we are removing 3,000 liters every minute. So if 1,000 liters is a meter cubed, that means we're removing 3 meters cubed every minute. So that sounds about right. If the diameter is 2 meters and we remove 3 cubic meters every minute, then the level is going to go down about 1 meter per minute. That seems about right. It's good to check like this to make sure we are not 10 times too big or 10 times too small. But then we can also check 10 meters. Well, in that case, there's an r squared in the bottom, so we have to divide by 100. So the rate is quite small. So let me tidy this up a bit so you can see. So in fact, that's minus 0.95 centimeters per minute. Okay. Oh. Oh, so I'm trying to add a new page. Yeah, there we are. So, another example. So in this example, we have a police car chasing a thief. Yeah. So here's the police car. So the police travel at speed 60. Let's not worry about the units for this one. And observe thief moving away at speed 20. As they go around corner. So what is speed of thief? So this has been drawn in the picture. The police car is on the y-axis and the thief is on the x-axis. Police car is going at speed 60, so dy by dt is minus 60. And they know, using some device, maybe it's a sound sensor, that the thief is moving away at speed 20. So ds by dt in the picture is 20. So how are x and y and s related? Just Pythagoras gives us that x squared plus y squared equals s squared. So as before, let's differentiate with respect to time. So again, we have to think what is changing. So x and y are both changing, and s is also changing. So x is a function of t, so we can use the chain rule to get the derivative of x squared as 2x times dx by dt. And the same for y, and the same for s. Because x, y, and s all functions of t. So we know everything in that equation except dx by dt, and we can use it to find dx by dt. So we can do that in the next after this 5-minute break. Thank you. Hi, let's continue. So, I need to share my screen again. So request to go back and look at the tank question. Here we are. So let me explain this in a slightly different way. So we have this equation relating V and R and H. So in this case, R is constant and H is a function of time. So when I differentiate this equation, then the derivative of the left-hand side is, of course, dV by dt. That's just the definition. But the derivative on the right-hand side is also really easy to calculate, because the right-hand side is just a constant times h. So remember, r is a constant, so 1000 pi r squared is also a constant. So we have differentiated the right-hand side. It's really simple to do that, because the right-hand side is just a constant times h. So, great. Yeah. Okay. No, so I made it a bit more confusing by making this error the first time round. I'll write this up more clearly when I publish the notes. But if R is changing but H is constant, then this formula holds. So if we had a tank where its radius was growing, then we'd use this formula. If its height was staying the same but its radius was growing, then we'd use this formula. So you have to think about what's happening in the question when you do this differentiation. Okay. So continuing the second example, where the police car is chasing a thief. So we now have this equation relating all the variables and their derivatives with respect to time. So what do we know? I'm going to make another copy of this picture, I think. So we can see so we know X and Y. We haven't been told S, and we know dy by dt and ds by dt. And we want to find dx by dt. So dx by dt and let's start with x times dx by dt is s ds by dt minus y dy by dt. And that is the square root of x squared plus y squared times ds by dt plus dy. Oh, I mean dy by dt here. So now we can substitute in. Well, x is 0.8. And the square root is of 0.8 squared plus 0.6 squared. ds by dt is 20. Y is 0.6. And dy by dt is minus 60, so I'm just going to put a plus there. Okay. And how to calculate that? Well, there is a right-angled triangle with lengths 3, 4, and 5. And so if I scale that, I can do better than that. So if I scale that, I get a right-angled triangle with sides of length 0.6 and 0.8 and 1. So this right-hand side is just 20 plus 0.6 times 60, which is 36. So dx by dt is 56 over 0.8, and multiplied by tens, I get 56 over 8 times 10, and 56 over 8 is 7. So the answer is 70. So let's go back and see, does that look about right? So the police car is going at speed 60, and the thief is going at speed 70. So 10 units faster. So you'd expect it to be the thief to be moving away at 10 or more units. So that's about right. At least it's not 10 times too big. Okay. But of course, you could not even start calculating this without calculators. Okay. So, a further topic, the linearization of functions. So say we take the tangent of y equals fx at x equals a. and say the equation of that tangent is y equals Lx. So that's L for line. Then it's obvious from a picture that x close to A Lx is a good approximation to fx. So for example, I have something like the x squared function and I have this point one, one, and then the tangent at that point so this is fx and this is Lx. And we can see that the x close to A, this is A, and then L and F are close. So this is a useful thing, and because the function may be very hard to calculate, but the linearization can be easier to calculate. So definition, if f is differentiable at x equals A, then the linearization of f at A is, it's the function Lx that gives this tangent. So the line through the point A, FA, with slope f prime A. And we say fx is approximately equal to Lx, and this is the standard linear approximation. So let's do an example to show how this can be useful. if I take fx is the square root of 1 plus x at x equals 0. So what is f prime x? Well, we use the chain rule. So first we differentiate the outside. Square root, the derivative of that, is reduce the power by 1 and multiply by the power we started with. So we multiply by a half, and square root is power a half, so we take power minus a half. So that's the derivative of the square root function. And the chain rule says put in what was there before, the inside, and then differentiate the inside. But the derivative of 1 plus x with respect to x is just 1. So we get this by chain rule. Now, f prime 0 is a half, so the standard linear approximation Lx is f of a, or what's that? So f of 0 is 1. So we take 1 plus a half times x. So we can see this is useful by looking at a table of values. These. So here we're taking for x, we're starting with 0.2. And then we're taking smaller values of x. And this approximation, square root of 1 plus x, is approximately equal to 1 plus a half x, the standard linear approximation. Does very well. So if x is 0.2, then the approximation, the linear approximation, is less than 100th away from the true value. As x gets smaller, it gets even closer. So another example. Which is useful to calculate one plus x to the power k if x is small. So f prime x by the chain rule is k times 1 plus x to the power k minus 1, and reduce the power and multiply by the power. And so if I calculate f0, that's 1, and f prime 0, that's k, then I can put these into the standard linear approximation, and I get Lx is 1 plus kx. So 1 plus x to the k is approximately 1 plus kx if x is small. And another example. If fx is 1 over 1 plus x, well, the derivative, again by the chain rule, we have 1 over something, so that's power minus 1. So to differentiate that, we multiply by the power minus 1, and we reduce the power by 1 to get power minus 2. And then the chain rule tells us to put the inside part into that. So f0 is 1, and f prime 0 is minus 1. So Lx is 1 minus x. So 1 over 1 plus x is approximately 1 minus x if x is small. So another useful tool for working with small changes are differentials. So let's define these. So remember, dy by dx is not a ratio. So it's not one number divided by another. But we do introduce variables dx and dy such that if their ratio I'm going to be careful, so dy divided by dx exists, then it equals the derivative dy by dx. So note, this can be confusing. write like this. For historical reasons. Going back to Leibniz. So let's give the definition. So in this situation, if y is a function of x, dx is an independent variable. And dy is f prime x times dx, if f prime x exists. So just to be clear, I should say, take y a function f of x. So that makes it very easy to write down what dy is. So for example, if y is x to the 5 plus 37x, then dy is f prime x times dx. So that's 5x to the 4 plus 37 dx. So for instance, if I take x to be 1 and dx to be 0.2, those are both independent variables, and they give dy is 42 times 0.2, so 8.4. So interpretation. So let me explain this in words. Let dx be a change in x. So say from x equals a to x equals a plus dx. So consider, like we did before, this linear approximation L. Well, it's given by f at a plus f prime at a times x minus a. So then we have, remember delta x means the change in x. So that's from a to a plus dx, that's just dx. What's the change in L? So if I change from x equals a to x equals a plus dx, then the change in L is f prime a times dx. But change may be different. So the change in y is f at a plus dx minus f of a. And that's equivalent, if I rearrange the equation, to f at a plus dx is f of a plus delta y. But if f is small, oh, sorry, I mean if dx is small, then fa plus dx is approximately equal to fa plus dy. And that's because remember dy is f prime x times dx. So maybe it helps to draw a picture for this. So we have this function and we have the tangent at some point. Well, let me make it curve a bit more. The tangent at some point like this. And I want to make 2 copies of this graph. So here is fx, the function, and here is Lx. And let's make this point, this point A. Then, if I have a small change in dx, then so here I have this small change in x, dx, and here I have the resulting change in the value of f. So that's delta y. But when I look at the linearization Lx, and I make this small change dx, then the change in Lx is dy. So that's how to think of this differential dy as dx changes. So it's not the same thing as how much the function changes, it's how much the standard linear approximation changes. Okay, so let's finish with a quick example to see if there are any questions on this. So, for example, if R changes from 10 to 10.1, then estimate the increase in A equals pi r squared. So these pictures show what we can do. So note we want to, well, how to say it? So the actual change the actual increase is delta A, but we can easily calculate dA as an estimate. So dA is A prime S dr. So let me take A is a function of R squared and approximate at S equals 10. So dA is this, and that's, well, the derivative of A is 2 pi R, so that at S is 2 pi S. So we take 2 pi S dr, and now dr is 0.1, the change in R. So dA is just 2 pi times 10 times 0.1, which is just 2 pi. So remember the standard approximation, the area at S plus dx is approximately the area at S plus dx. So the area at 10 plus 0.1 is approximately the area at 10 plus 2 pi. So that is 102 pi. So we can calculate the area at 10.1, that's pi times 10.1 squared, that is 102.01 pi. So delta A, is 2.01 pi. So close to dA, which is 2 pi. Okay, thank you, and see you on Monday.